Okay, just let me try it.
Yeah, please, sir.
I guess you cannot hear it.
Yes, sir. Actually, when you have shared the screen, you have to just, when you click on share, there is some option of include sound, then we can hear. You please stop sharing.
Yeah.
And then you click on share. And now there is something written include sound. Yes, then we will be able to hear. No, sir, actually, we are not able to hear it actually. Yes, we got it, sir.
So,
Yes, sir, we are able to hear. Yeah, we are
Yeah.
able to hear clearly, sir. Yes.
Yeah. But now I have the problem. Okay. I have little feedback, but you don't have feedback. For you, it's okay.
Yeah, for us it is okay. Yeah.
Okay. Yeah. So, well, what have you seen here? Yeah. You see here the SPX. So that's the S&P index. Yeah. That's the
Yeah.
flat line here.
Yeah.
This one. Yeah. On the day. And then the VIX, that's a volatility index. I will explain. Yeah. Which is just one level. But what you have seen here is a volatility smile at each time point. Yeah. And you see if it's probably here in the middle, it's in the money. That's like if the option execute, you get money.
Yeah.
You get a volatility, implied volatility. And if out of the money, it's getting high. Yeah. This means out of the money, you don't earn money yet as an option holder, but you might earn a lot of money in future. So the bank will charge you a lot to buy this option, because even if the probability is small that you make a lot of money, you will make a lot of money and you have to pay for this. Even the probability is quite low. So this means implied volatility is high.
Yeah.
So first you see implied volatility is not one figure. Implied volatility is the entire curve. Actually, it's a surface. Here's the development in time, and we will go on until we see a real crisis. Now this explodes when a crisis comes.
Yes.
I don't know whether you have followed, but the VIX was usually around 20. I told you 20 is a good number for implied volatility. Yeah. Here in crisis October 2008, it went up to 70.
Yeah.
Even it's
Yeah.
low. Yeah. The average of these lines, it was burning. Lehman Brothers was burning. Yeah. You
Yes.
already
Yes.
saw it in the surfaces,
Yes.
in the implied volatility. Yeah. It went up.
Okay, so the object
Yeah.
of today's presentation is the IVP model. So IVP standing for Implied Volatility Surface Parameterization. And we will be applying that specific
This was an example of implied volatilities.
Yeah.
Now I have the problem. I have my feedback here. So how do I? Probably I enter again the other one. So I open the other one again and say micro off. Yeah.
Yes, sir. Yes, sir.
Okay. So this movie should have motivates you really to understand implied volatility, because implied volatility tells you about the risk in the market. So implied volatility, I mean, okay, so we first have to finish this part on the Black-Scholes partial differential equation. So we know how to get VTX as a solution to this partial differential equation. This was what we have seen, this one. So the price, when it's a unique one, so this means in order to get the price, we have to solve this PDE. And that's why PDE method, numerical PDE methods, are also used for option pricing. Like finite difference scheme, typically partial differential equations, one numerical method to solve this is a finite difference scheme. The other one is actually this tree method. The tree method of CRR is also one solution, one way to solve this. And it's basically because these solutions are actually what's called the green functions of solutions like this. That's the transition density of Brownian motion. So the green function, at least associated to the Laplace operator, that's a normal distribution. And if you have different diffusions, the densities are also the green functions of partial differential equations like this. So if you don't like probability, put it like this, you just believe an equation like this, and then you solve this partial differential equation. But in order to understand why this PDE is truly connected to financial markets, it's useful to understand the underlying probabilistic arguments. Okay, but nevertheless, we finally get, and that's the Black-Scholes formula. The Black-Scholes formula we have seen before. If our F equals the option payout of if the F is these, hold it somewhere. If F is the option, it's the payout of a European call option. So this was the Black-Scholes formula we have already seen. The Black-Scholes formula on an exercise. You can prove that this Black-Scholes formula, which we have seen, I think, quite early when we did the CRR model, in the binomial approximation. I show you the Black-Scholes formula. So this function, I now just denoted Vt of S. So S is instead of S is our X. This function with T minus T here. T minus T time to maturity, T minus T, T minus T. This function VTS solves PDE. No, you can either believe the lecture or you can do just the calculation. Huh? You can take the second derivative out of this because at n of, call it y, equals minus infinity to y. Huh? So you do the calculation and you see that Vtx solves the partial differential equation with the condition that Vt of S equals S minus K plus. So we have now derived this Black-Scholes formula from two angles. Anyway, the common term is this is expectation under the we don't have to do the risk neutral measure here. We just know that's integral minus infinity plus infinity payout function x minus k plus under, we can either put it like this. So we take here our sigma squared t minus t dx. And here we have the normal density x. So this looks like complicated integration, but what is this the expectation E star st minus k? That's a value discounted. T. So this expression, the risk neutral expectation, that can be either derived by the approximation or derived from the Black-Scholes partial differential equation by the general theory of the connection between PDEs and stochastic equation, or here explicitly we do all the calculations for the Brownian density. Okay, but nevertheless, we now go to this formula. Again, this is the Black-Scholes formula. Do we just denote it? Just to keep it in mind. This is a function. Now K is in the contract. Time is also deterministic. R is deterministic. We just consider now the Black-Scholes formula. Xi T K. Price Black-Scholes of a call maturity T. Call it time to maturity. We also consider time to maturity. Okay. And now we consider it as a function of sigma only. Let's call it also from ST. S0. From S, that's a price at time t. So that's basically a function of sigma, because what we do in implied volatility, we just figure out, we invert the problem and just say, okay, we get the implied volatility for market. We get the volatility sigma for market prices. Now that's what's called the calibration. Okay, that's now kind of how this formula works in practice. Huh? Model calibration implied volatility. As I said, everything is fixed. We also agree on the interest rate R. Huh? Let's say we get a zero coupon. For example, we take the rate until time maturity. Yeah, that's the zero coupon bond I shortly we talked about. Huh? So R is not disputable, or R is in the contract, put it like this. Huh? So now we still have to get sigma, and so most people just start, okay, I take the historical volatility. No? That's called the historical volatility. But basically, what does it mean? If you just take the historical volatility, it more or less means you are just on average get the same amount as if you do a riskless investment. Even on average, you get the same if you take the historical volatility. Nobody would take risk to earn the same money as if you would invest in a money account. There's no reason for an investor or for a bank to sell or buy an option which just gives you the same amount of return as you have done historically from any other investment. In order to take the risk to write an option, you want to be compensated for the risk. And that's usually because it's increasing, like call options, prices are increasing functions of volatility of this parameter sigma. I call it now just a parameter in the pricing formula. So this is, you have increasing function. So this function, Scholes price is increasing in sigma, all others fixed. If sigma increases, the price increases. So in order to be compensated for taking, let's say, the historical volatility as risk, because you're not forced to take it, but if you want to persuade it to take this risk, like a bank, the bank writes this option because, let's say, like on typically it's currency, because like other companies not in financial, like automotive industry, they don't want to take the volatility risk. They are happy to pay some, let's say, some fee like add-on that they don't have to carry the currency risk. So they buy a currency option, so they have a fixed or a minimal fixed exchange rate. But if the bank would just take the historical risk, bank wouldn't write this option. He won't be. The bank would like to be paid for this, and so he, at least in theory, the bank just put in another parameter in the Black-Scholes model, and that's what's called. You calibrate this one to market prices. So for each market price, the V superindex M, superscript M, now means market prices. These are just the market in the prices. And then you figure out the parameter sigma implied in the Black-Scholes formula. That's the Black-Scholes formulas in V0 equals this pi CTK sigma implied. That's our Black-Scholes formula. And this equals F0, Fn, sorry, Fn. Yeah, so sometimes you also say you put in the wrong parameter in the wrong formula to get the correct price. Just a way to quote this because it's so conceptually so powerful, the Black-Scholes formula. It's a way to transform a price into some opinion, put it like this, about risk or valuation of risk. That's how you get implied volatility. Okay, then this small lemma tells you, under some conditions, you always find, so that's the derivative of option price, what's called vega. We have already seen that the dc to ds, that's the delta of option. And this one is the vega of options. And then you can calculate it. That's our Black-Scholes formula, and we see it now as a function of sigma, and we can differentiate it, and we can solve numerically. I don't know whether you have numerically you can solve it, or you can, if you think numeric is kind of not a very fancy name, you say, okay, I now take an AI method to fit this sigma implied to get out of this function. There are also now AI methods how you get these functions, because you will see okay, so here you see that you get the sigma implied under some conditions. What are the conditions on, let me see. So this is a Black-Scholes formula, and then you can differentiate it. And then so this means for the call options, this is positive. Phi prime is a density, sigma 0 is positive. So this is a positive. If sigma is positive, so on the positive volatility, this parameter sigma is always positive. Phi prime is a density. Density is always positive, so it's always positive. So this means it's an increasing function. So for each, you can invert this function, inverse function. Sigma exists, but we have to do it numerically. So at the end, so it's strictly increasing this function. Sigma goes to option price. What we do, we now go from the space of volatility to option price. If V0 is a market price in this interval, okay, that's the boundary condition. Because this maps C, the image of C is this one. The image of this map C. You can only invert prices if they are between S0 and S0. But that's clear. Also under arbitrage condition, if you look at an option price lying outside this, will give you an arbitrage. Okay. This would be more or less the immediate execution of the option. So then you just have nothing from the option. If you immediately execute, you shouldn't do it. And so that's the maximal price today you get anyway. Options price must be in between this interval. And so that's called the implied volatility. It's a wrong translation. Of course, this inversion, you need a kind of a numerical procedure to do this. Actually, there's no closed form solution, even if you write it as closed form solution, because you have always the normal density, the normal integral, and so on. E minus 1/2 x squared only exists numerically. I mean, that just closed form solution just means, okay, you take those formulas where you're used to. Because usually these functions are just, in a computer, doesn't calculate these functions, it's just a table. There's no closed form solution. Whatever you mean with closed form, I don't know how you discuss this issue, but what is a closed form solution? This looks at a closed form solution, but numerically it's not trivial to get this. It's a table. In this sense, it's trivial. So now you see, of course, that's the market. That's why I say you put the wrong parameter in the wrong formula to get the price. Because it was asked, what is the physics behind this? The physics behind it are just the prices. Physics in terms of observable, the observable in the market are prices. Any model you have has to reproduce the prices if you really want to apply it. So this means you now get one price, let's say of a call option fixed maturity, and we have the price K1. At strike K1, you get a market price at TK1. And you say, okay, that's a Black-Scholes price, it's an implied volatility. Then you take this implied volatility and price an option at TK1. You put into Black-Scholes formula this option, this implied option from strike K1. And if the model is correct, of course, this should be the market price also at another strike. Because the Black-Scholes formula has just one volatility, the volatility of the underlying asset. That's not true. That's why I say how it's used, Black-Scholes formula. Black-Scholes formula is wrong. So in order to fit it to the market for each instrument, you should put in another volatility. Even volatility is associated to the asset price, and there's only one asset price. So the use of implied volatility more or less tells you the formula you're using by calculating the implied volatility is essentially wrong. Not correct, because don't claim market price. But then you somehow have an asset price, which if you consider is associated to the at-the-money call, you get the at-the-money volatility. But if you take an option with twice the current price, out of the money option, then you should take a different implied volatility. If you believe the model, this means then suddenly your Brownian motion and the geometric Brownian has a different drift. But the drift of Brownian, the volatility, the standard deviation of Brownian motion should not depend on the options which are traded on this Brownian motion. And this is what we have seen in the previous example. I don't know which T they have taken. We have seen several. This means this actually is V0. at sigma implied, but on T K2. And so this means at each different maturity and each strike, you get a different implied volatility. That's why it's a surface. At each time T, or each trading time, today you get an entire option implied volatility surface. This means you get fixed T, you get what's called the smile. But the smile will also change. It's actually a skew. It depends on the market, so but it looks like smile. So these are at the money. Implied at the money and here out of the money. So that's S0. That's our current value. At current value, sigma implied S K equals S0. That's usually the lowest one. And so you get for puts, you get other, you could put implied volatility, you could call implied volatility. Yeah. So all the trading, all the traded prices are associated to different volatility parameters called implied volatility. But nevertheless, it gives you, this was, when this came up, this was a way, kind of an objective and common agreed way in the market to express your opinion about the risk in the underlying asset. Okay. But of course, mathematicians are smart, and if you have done, because most people working in mathematical finance have done probability theory 10 years before or 20 years before already. Yeah? So they know how to fix this problem. They said, okay, our geometric Brownian motion is too easy. And this was done by a person, Dupierre, who was actually a trader. And it's still a trader, or not a trader, what's called a quant. The mathematician supporting the trader. Dupierre, he developed this local volatility model. The local volatility models were developed, or at least first published by Dupierre. I mean, from a stochastic point of view, okay, that's clear. You have just another stochastic equation where you have now, instead of just one parameter, you also have a surface. Sigma depends on time and space. So sigma also goes from R plus 2 to R, the same as your implied volatility. I mean, that's also a function which goes from RT to R, giving each maturity and each K a real value, namely the volatility, also to R plus. Everything is on R plus. And so you have, your model is rich enough to capture this. And you also know you have a transition density, you have this Markov process series, you actually can fit, then you price, so you actually get, in this model, there's a self-financing strategy. So that's why we have to learn it more general, not just for black Scholes. That's why we have to understand the concept more broadly, in order to apply it in reality. Just learning geometric Brownian motion with fixed sigma doesn't help you in real life. Of course, it helps you in real life, but because these models are also implemented. But this one, if ST is now your asset value process, when does it have a solution? You have some regularity on sigma, so your sigma implied, your fitting of the sigma implied, because sigma implied is also known only at discrete points. You need a smooth surface to fit it, and so on. And if this is smooth enough, if your sigma, for example, you can imagine, because you have to do this partial differential equation, at least this sigma should be in C2. But nevertheless, in this general model, whatever sigma is for the general theory, you just need existence of this solution. Then you have to prove there's a martingale measure. Of course, this is a martingale measure. As you can imagine from the Gezanov transformation, sigma is not influenced. So the general Gezanov transformation I showed you at the beginning also covers this case. Whatever you start with drift, you have to, your martingale measure always looks, you might have started with mu of t or whatever, but by Gezanov transformation, you always risk neutral martingale measure always means that's your drift. Your p star, of course, comes from a different p if you like, but at this level you don't care, because you know the same principle works for more general diffusion process than just a geometric Brownian model. And you again solve a PDE. The PDE, the feature is this one. Now depends on time and space. Okay. So this means this local volatility model, we have the formula. Yeah. You see the formula, how the sigma, let's assume you have this C, which is, you have calibrated this surface. Currently, today, you have calibrated surface. You have options with maturity T. You have options with, these are your option price. Then this would be your local volatility. CTK you get from market, if you like. Market calibrated for market. So this was a nice cloud you have seen in the movie. And if you don't care about mathematics, you stop here, but as really to understand the market, you now can assume, okay, then my asset price is not a geometric Brownian motion, it is this local volatility. DST is an RST dt plus sigma TST ST dWt. And then that's correct. Then you plug this in here and you get the proper call prices. And that's the PS formula. And so, of course, we have now the problem if you have a market where you have put options, where you have path-dependent options. So in application, you always need even a more complex underlying asset. You have a big market with even more products. So the first step in financial engineering, an application of these risk-neutral pricing, you find a stochastic process that today prices are matched. That this holds for all prices, all option prices. More complex models for S. That's what calibration of a model to the market. Your model, like in physics, your model should explain the current state of the world, at least. In the context of financial markets, and your model, like this one, even more, you can add jumps if you like, you can add time dependency, you can add path dependency, it can also depend on the entire path, you can take other driving noises, you can take rough volatility and stuff like this. There are many extensions of this, and like before the crisis, actually the option markets were even larger. It was even more challenging to find models which you never will find a model which you always have the optimization problem. You have market prices, many, and you have market prices, many. So you want to take, then it's already close to statistical learning or whatever. You want to have many different, for each instrument, many options, and you want to minimize. Find a parametric, put like this, if you like a parametric. That's, you see, this looks already very much like a machine learning problem or whatever. You have many prices, and you want to fit a function to this and minimize. You can say, okay, I don't care about mathematical finance. I say my model prices are just neural nets, whatever. And you can, most people don't do it on prices, they do it on implied volatility. They have many implied volatilities here for each instrument. But implied volatility is just a way, it's quotation, how you quote options. You quote options in terms of the implied volatility. And if you get the quote on the implied volatility, you put it in the Black-Scholes formula, and then you get the actual price. And of course, it makes it different because it's a non-linear transformation, whether you want to have deviations on the implied volatility or your errors are on prices. But so this is like disputable in many cases, whether it's better to fit the option surface or it's better to fit the price function itself. Depends on your taste. I don't know what you do in machine learning or whatever, but nowadays many people doing this, figuring out this theta in a class of fitting functions in order to get a minimal deviation. Then they get a price function for options, then let's say depending on T and K. And then they said, okay, if I have now an option which is not traded, I just take the value of this TK. This is always used for extrapolation because you always make most money with options which are not traded yet. Okay, so I'm finished with this tutorial.
Okay, sir. So thank you so much, sir, for this wonderful lecture. And we will be starting after 1 hour, Indian time at 2:30. German time at 11 a.m. So we'll meet at 2:30 p.m. again. All the participants are requested to join again. We are winding up this